Hello everyone. Let us continue our discussion on system modeling. In the first lecture, we had considered single phase transformers. Now, in common applications, the transformers are three phase, and or we can use single phase transformers, three single phase transformers to be connected in bank. And so we consider here the three-phase connections of transformers. So the first one is the YY connection. So we have three single-phase transformers. Okay, this is the first one. Okay, this is the second one and this is the third one where each transformer is represented by two groups of windings, no, the primary and the secondary. Now, if we have three single-phase transformers to be connected for three-phase operations, and the first connection that we're going to use is the YY connection, meaning we connect the primary windings in Y and the secondary windings also in Y. Now, before doing the connection, we have to consider the polarity of the transformers, because this is very important. Otherwise, if we commit mistakes in making connections because of wrong polarities, then a short circuit may occur in the windings of the transformer. So we have to verify first, or we have to be sure, the polarity markings of our single phase transformers. So assuming that the polarity are well indicated in the casing of the transformers. So for transformer 1, we have for the high voltage side, we have H1 and H2, and on its low voltage side, we have X1 and X2. Now similarly for transformer 2 and for transformer 3, we use H for the primary and X for the secondary. Now to connect the primary winding in Y, we have to connect the each two ends of the windings together. Okay, so we have here a common connection of the each twos, and then the supply lines will be coming or will be going to H1. So we have here, the second is here, and this, we have the third, and we connect the supply voltage here at the primary. Now similarly for the secondary, we also connect them in Y. So their X2's terminals are connected together at this point, to form the neutral. While for the supply lines, we obtain that from the X1 terminals. Okay, now as to the transformation ratio, the primary line to neutral voltage is equal to the primary line to line over square root of 3, and similarly for the secondary line to line neutral voltage is the secondary line to line over square root of 3. Now the transformation ratio is defined as the ratio of the voltage per phase, no, of the primary to the secondary. So it's just the same. Okay, when we substitute, the line to neutral voltage here equal to the primary line to line voltage over square root of 3, and also here for the secondary line to neutral voltage is equal to the secondary line to line voltage over square root of 3. So the square root of 3 will just cancel, so we just have this one. Now this kind of connection is very appropriate for protecting our transformers from short circuit currents or faults, because the windings are both connected in Y, and we can provide grounding to the neutrals both at the primary and at the secondary. So when there is ground connection, so short circuit currents can just flow to the ground. And then secondly, for this kind of connection, we can have dual supply voltage, because we can bring out the neutral outside to form another terminal here. So first we have the line to line voltages, so we have the line to line supply voltage now. And then since we have the neutral being brought out, then each phase, okay, line to neutral, okay, line to neutral voltages are also available, which is another set of supply voltages. So, okay, two voltage levels will be available at our secondary terminals. Now, the second type of connection is the delta-delta connection. No? We connect the primary windings in delta and the secondary windings also in delta. So we have this symbol delta-delta. Now, to connect the delta connection, okay, for at the primary, you have to connect H2 to H1 of the second transformer and bring that out as a line or as a terminal, and then we connect H2 of the second to H1 of the third, then bring that also outside as a terminal. Then also H2 of the third will be connected to H1 of the first, so we have another line here. So we form a delta in this case at the primary. Now similarly, at the secondary, we also connect X2 to X1 of the second transformer, then X2 of the second to X1 of the first, and bring that out. And X2 of the third to X1 of the third, and bring that out. Okay, to provide connection for our three-phase loads. And the transformation ratio here for delta delta, okay, is just equal to the line to line voltage at the primary over the line to line voltage at the secondary. Now this kind of connection is very applicable when our load is unbalanced. So when we have unbalanced load here, okay, the line currents towards the loads are also unbalanced. And to make it stable, okay, the primary windings being connected in delta will somehow, okay, neutralize, okay, any unbalances, okay, of the fluxes, thereby also in the induced voltages in the secondary windings, okay, to make the system uh, stable, okay, due to unbalanced, okay, currents. Okay, the third type of three-phase connection is the delta Y. No, meaning we connect, okay, our primary windings in delta as we have illustrated before, and also the secondary winding, okay, in Y as illustrated also before, and the primary, the transformation ratio, then okay, basically from phase voltage to over a secondary phase voltage. So we just have square root of 3BP line to line over BS, okay, line to line. Now this kind of connection is appropriate for takeoff transformers at the plants now where we want to step up, okay, the generator voltage usually from 13.8 kV to a high voltage of 138 kV. So the high voltage side is Y connected and the low voltage side is connected in delta. That is to minimize or prevent so much stress, no, in the windings of, okay, the transformer when we connect this in Y. Now the fourth, okay, three-phase connection is the Y delta connection. We connect the primary windings in Y as we have discussed, okay, before, and the secondary windings will be also connected in delta, as we have seen before. And then the transformation ratio, okay, would just be, okay, basically from primary phase voltage over secondary phase voltage. So the primary phase voltage is the primary line to line over square root of 3, and the secondary phase voltage is just the secondary line to line. So in effect, our transformation ratio here will just be equal to 1 over square root of 3, okay, times the ratio of the primary line to line voltage to secondary line to line, okay, voltage. Now this connection is suitable at the end of transmission lines. So since transmission lines are at high voltage, so we have Y connection of the primary, okay, to be appropriate and at the secondary we can connect okay the windings in delta, uh, especially when we expect the loads of okay our system to be unbalanced. So it's better to have a delta connection here for stability. Now the fifth connection is what we call as the VV, or the open delta connection. Now this kind of connection is resorted to when we have only two single phase transformers and the existing load okay, can be served by the two transformers. So it doesn't warrant for additional transformer okay, for a three-phase connection, since the load is still small that the two transformers can still serve. So uh, we have this connection. Or another case is when we have okay, three transformers connected for three-phase operations, and then one transformer okay, fails, then we can reconnect the two transformers remaining and open delta to serve okay, partially okay, the load, although it cannot serve the total load as the three transformers serve, but we can reduce okay, the load and serve a part of the load, so it's not total okay, blackout okay, for the system. So when we have okay, two transformers connected in open delta, okay, the connection is just like this. Now we connect H2 of the first to H1 of the second, and then bring that out to be the third line, where the other two lines are coming from the H1 terminals. H1 of the first and H2 of the second. Now similarly for the secondary windings, our okay, we connect X2 of the first to X1 of the second, and then bring that out, and then the other lines will be from X1 of the first and X2 of the second. So still this is balanced okay, three phase okay, power supply.